Hello everyone, Mr. John here from Areteem Institute with this week's Thursday Tidbit, where we have a few more AMC 1012 problems to review. Now, these problems are taken from the B-Date tests, which was November 16th, yesterday if you're watching this video right as it premieres. And I want to give a quick plug to our blog where we have the answer keys there, so you can use the answers to check your questions. Which ones did you get right and wrong? Check what you think your score should be based on the official one, just to make sure things are okay there. But also the different topics and concepts tested. So you can see which ones covered more algebra topics, which ones were geometry, and maybe what theorems were helpful or what you want to review there, things like that as well. But let's jump in right away to our questions. We have the first question appearing on the 10B as number 24. So we have these functions and we're given a couple pieces of information about them. So first of all, we have this bound on the functions, right? So how far the functions can differ based on how much their x inputs differ there as well. Now, we'll do this algebraically first, but I want to point out now, and we'll look at this a little bit in a second as well, just in terms of how can you interpret this on a graph, right? And if you divide by x minus y, it's not too hard that this is really some type of slope restriction, right? So the slope of these functions at different points is less than or equal to a half. Now, only other piece of information we have is we are looking at f of 300 equaling f of 400. And as soon as you see something like this, right, you say, well, if they're not telling us the specific value, it probably doesn't matter. So just as something to keep in mind and something to help us visualize, to help us work with those things a little bit, let's choose our favorite number for that. You could pick whatever your favorite number is, but there's a best favorite number in this case, and that is 0, right? Because now our inequalities become a little bit nicer from there, right? So if we're looking at how far things kind of differ from that point, right, we can get some information there as well. So let's take a look at our actual question. So our actual question is, what is the greatest possible value? So I want to just highlight that here as well. And we're looking at the greatest possible value of f of something minus f of something there. So as soon as we see those nested f's, right, things get a little bit complicated there. But we probably want to take things one step at a time, and we can look at those inner things, right? So we have f of 800 and we have f of 400 in this case. Now, we could write restrictions in different places, but it should be fairly intuitive that, right, f of 800 is close to 900. So if we want to look at something about f of 800, we want to compare it to f of 900. So we'll do the first one in a little bit kind of more detail here. But if we look at our restriction then, right, we see f of 800 minus f of 900. And here's where you kind of see why us choosing 0 was the quote-unquote best choice there, because this is going to simplify nicely, and then this is less than or equal to 1/2 times the absolute value of 800 minus 900 there. So let me make that absolute value a little bit more pronounced in that scenario so we don't confuse it with a 1 or something. And the advantage of this then is what this is really telling us is that f of 800 is less than or equal to 50. So, right, and just because we had 0, it could still be absolute value. So the absolute value of f of 800 is less than or equal to 50 in this case there. Right? Why is that? Because we have this f of 900 is 0, matching f of 300, right? And you can kind of see here that we're really just saying how much they differ from 300 or from the f of 900. So let's just keep our baseline nice, and we can do something similarly for the other one. So let me not write out things there. So similarly, f of 400 in absolute value. Again, that differs from 300 by 100 divided by 2. This is less than or equal to 50 as well in that case. Now, right, we're looking for the greatest possible value of, right, these two things there. Right? And so if we look at this, right, I don't want to write out all of the details. Let's kind of maybe say some of this verbally and things like that there, right? So this is going to be, right, possibly largest, right? Or what's our goal here? Well, the difference is less than or equal to the changes of the x's there, right? So maybe let me write it out this way. So, right, this expression, right? So f of 800 minus f of 400, right, is less than or equal to 1/2 the absolute value of the inside. So f of 800 minus f of 400. Now, here's where, right, we can look at our bounds there, right? So in absolute value, both of them are less than or equal to 50 there. But if we want them to differ by as much as possible, right? Well, one of them can be positive, one of them can be negative. So we could have something like 1/2 of, well, maybe f of 800, right, is going to be positive, and then we kind of have a negative there as well. So we could have 50 minus negative 50, and then this is equal to, well, it's less than or equal to 50 itself. And so we would have that this thing has to be less than or equal to 50 in that case there as well. So that's kind of what we're looking at here, and that's going to give us answer choice B. Now, you might be a little bit weirded out and say, well, how do I know for sure that we have enough, right, time, and that'll make more sense in a second, or how do we know it's actually possible to get this difference of 50 there, right? How could this kind of function work? What is this going to look like, or things like that as well? So let me kind of clear some of this off of the screen in this case, right? Namely, some of these things on the bottom. And I want to kind of interpret this. Remember, we can interpret this graphically a little bit as well. So let's look at some graphs here. So remember, we said this is thinking about slopes. So, right, let's look at our graph here. So let's interpret these things as slope a little there. So, for example, we had this idea of f of 300, right? So f of 300 we said was 0. We said f of 900 was also 0 there, right? And so then we were kind of looking at these, right, and saying, well, how could this stuff change, right? How could these different functions change? And notice that we can interpret this as slope. So for example, moving away from 300, these lines are plus or minus slope of 1/2. So actually anything in between this region is fine, right? Going the other way, right, anything in between here is also okay, right? And pretty soon we see they get kind of pretty big and small, and that's okay, right? So from this 300 value, right, anytime we have to stay inside of that kind of new cone or kind of triangle stuff, right, where we have this slope of plus or minus 1/2. If you added new points, you would still have to kind of make sure you always have a slope less than or equal to 1/2. But, right, in general, because we're looking for the greatest possible value, we want some extreme cases there too. So let's look at this for our other one as well, right? So we had this idea here where we were looking at then f of 902. And so this would give us some other restrictions that we need to live with. So anything inside of this kind of cone there as well is okay, right? But really the key is we're kind of inside these dotted lines and everything that's going on there. Now, what was the idea of the algebraic thing we just did, right? So the idea was we wanted to look at, right, f of 800 and f of 400, right? We wanted f of 800 to be as big as possible, which we said was 50. So where does that come on our line? Well, notice that that can show up on our line over here, right? So if we look at that on our line, we could connect the line with slope of 1/2. We could connect that to this point here. That is our point, right? We have f of 800 equals 50 there. And notice that we could do something similar for the 400 part as well. So if we're going to the 400, we said we wanted this to be as small as possible in this case. And so this was our value there of f of 400 was negative 50 there. Now, a couple of things to do from here is, well, what does the rest of our function look like? First of all, one worry is what happens in the middle of these two. So for example, is it valid to just connect these 2 points there? Is this okay to connect those here? Well, sure, right? That slope is okay there. Now, what we're doing doesn't really matter on the right endpoint. So maybe say we are increasing from there. So we kind of do this zigzag up then from there, following the dotted line up in that scenario. And it doesn't really matter what we do in the other direction, but I guess just for completeness, because we are doing f of 800, right? So now our difference is becoming f of 50, right? So if we're interpreting this difference here, this is becoming f of 50 minus f of negative 50. And there's no absolute values here, so let's be a little bit careful. So let's have our function zigzag down. And now we have, right, some of these values there, right? So you could check this or work through the details, kind of your stuff there as well, right? So in this case, then we would have negative 125 for the 50, negative 175 for the negative 150. And so that difference would be our 50, positive 50 in this case as well, right? Practically speaking, we don't need to worry all that much about the absolute values, right? It should be pretty clear. You can do some flipping and things like that as well if need be there too. But this is a good visualization of what this graph looks like and how things work from there too. Okay, so let's move on then to our second question here. So we have some circles in this case. This problem was both on the B for 10 and 12. So 22 on the 10, 21 on the 12. And we have a question about tangent circles in this case. So what are our circles? We have x squared plus y squared equals 4, right? So we have a circle with radius of 2. We will be using these at times, right? But let's just mention it verbally here. We have a circle with radius 8, and we have, whoops, let me do this in a different color for a preview, and then blue for our circle of radius square root of 3 with a different center. So that we have this center of 5, 0 there. Now, I want to have a pretty decent picture for us to work with, so let's use the magic of doing this as a video, right? And now we have our 3 circles there. So we have our circle of radius 2 in green in the center, brown, right, circle of radius 8 sharing that same center, and then we have this circle of radius root 3 moved off to the side with this center of 5, 0 and radius of radical 3 in that case. And we're looking for circles that are tangent to all 3 of these circles. So not 2 of the 3 or anything, all 3 of the circles. And we want to find the sum of the areas in that case. So let's kind of look at some notes and some observations of things we want to kind of look at here, right? So we do have this idea of internally or externally tangent, right? So pretty easy to see that if we have a circle, right, tangent on the outside of the big circle, right, this is definitely not going to work in that case, right? So, right, we might call this there, right, we have internally tangent to the large circle. So if we just kind of note this first of all, right, so note all circles are kind of internally tangent, right? So inside the circle of radius 8. So this is our note 0. This is kind of the first thing we want to say, first observation that's going to drive everything else that we have from there. Now, inside the circle, we have kind of a little bit more of something to figure out there. So, right, we could look at a couple of cases here, and let's focus on the green and brown circles. So what advantage do we have there? Well, for the green and brown circles, since they both share the same center, right, we have this nice line, and let me kind of exaggerate this a little bit here, right? We have this nice line that we can always draw anytime we have these tangents, right? Things like that there, right? So we have kind of 2 natural cases that we have here, right? So let me kind of just label these as cases there, right? So case 1, right? I'm not going to verbally label this with the internally, externally stuff, right? But this would be it's internally tangent to the brown circle, externally tangent to the green circle. Now, do we know the radii of these circles, right? Well, we do, right? So, well, we know the circle inside is 2, and we know the outside circle is 8. So let's let this circle here have some center. I know this isn't tangent to all 3, but I want to talk about symmetry in a second, right? So we have R and R. So in this type of setup, right, where we have kind of this externally tangent to the green, we have 2r plus 2 is equal to 8, because that is that outside circle there. So 2r plus 2 equals 8, and this tells us that we have a radius of 3 in this scenario, right? So in this scenario, right, we have this radius of 3 here as well. Now, I want to point out, moving around this picture a little bit, right? Actually, this is perfectly fine anywhere. Anytime that this circle is tangent like this, right? That radius is always 3 in this scenario. So now let's turn our attention to the blue circle in this case, right? And so let me just write out for what we need for the problem, right? So the area here is equal to pi r squared. So pi 3 squared equals 9 pi. And right, you could do this maybe a little bit more formally with some equations and stuff like that. But I think it's nicest, and I think it's just easiest if we look at this visually on the picture. So where could these be tangent, right? Well, here is a picture that it's tangent to both there. Now, we are going to always have symmetry. So if it's tangent on the top of these two, right, well, it's going to rest perfectly fine, be tangent on the bottom of these two there as well. But, right, think about, even if we're not labeling them these ways anymore, think about internally and externally tangent. So, is it possible to be internally tangent to that blue circle, right? So we're kind of inside of that circle there. That is fine. Quick check, is the radius of this purple circle we have, is it bigger than root 3? Yes. So my diagram is accurate. This is okay there. And again, we have a doubled symmetry here. Now, is there anything else that can happen? No, right? It's kind of tangent on the top and bottom in 2 of these configurations. So what we really have for our area here is this is times 4. So this can happen in 4 ways. And so the combined area for the 4 circles in S thus far are 36 pi in this scenario. So we have this one case there, right? So the radius was fixed as soon as we said it was the smaller radius, so outside the green, inside the brown, the radius had to be 3. And then tangent to the blue circle, that could happen in 4 ways. So what is our case 2? Our case 2 is the opposite, right? Well, not opposite, but it's inside the brown, of course, because we said that has to happen. But it's now going to be outside of the green, or tangent to the outside there as well, right? So this is what we have in this case here. And we can write down a similar equation. So we always want to look at this tangent line and think about the radii and stuff like that here. So what is our case 2, right? Well, this time if we do 2 of the radii, right? So we have 2, or we have a r, so the center is somewhere like here. We have an r. Then the other r is too much, right? So if we add a second r, that would get us all the way out here. But then we need to subtract 2 in this case. So now we would have 2r minus 2 is still equal to that radius of the brown circle, which is 8. And then if in this case we have, not surprisingly because we can see the picture, we have a larger circle of radius 5. So in this scenario, again, no matter where this pink circle is, no matter where I move it around, it has a radius of 5. So that is fixed in this scenario. What is the area here then? So the area is, right, let's skip over the squaring. We all know how to do that. 25 pi. And here, right, again, we can think of these as cases. Is the radius big enough to be inside or outside the blue? Sure. We have this configuration on the bottom. One on the top is going to be similar. We also have, whoops, let's not change the size of this, right? We also have, and this one you might be a little bit worried about, right? But you can again check this radius is big enough to fit around both of them, right? That's not too hard to check there, right? This radius, the diameter is 10. 10 diameter is plenty big enough to fit around both of these circles. So again, we have 2 times 2 equals 4 arrangements of this here. So we have those not same 4 arrangements, but similar 4 arrangements. And this gives us 100 pi area there. So the total of these put together, right, our total area, our total answer then is going to be 136 pi, which is answer choice E. So that's what we have then here. So this is a good problem, especially thinking about it, right, as a contest question. What do we want to do a little bit more formally? I think it's good to calculate those exact radii, right? So we know, okay, the circle is either this big or that big. But from there, I don't think you should do all the details of, well, where's the center of the circle in these scenarios, right? Maybe you set up some equations to convince yourself or double check, but you can do a lot of this visually there, saying, okay, there's going to be 4 places for both of these circles. What are their areas? Add them all up, and then we have our answer. Okay, that will do it for this video here. So stay tuned for some new problems and new questions next week. Right? Let us know if you have some requests, right? We're done with the AMC 10-12 season. The test just happened. Do you want to see some more of those problems? Should we do some additional topics, other math contests you might want to see problems for? Let us know below. And of course, subscribe if you want to stay up to date all of these things, and it helps us out that way too. Thanks for watching. Goodbye.